everyone. Good morning, good afternoon, good evening, and welcome to our ARM AI Virtual Tech Talk series. This is all about bringing brilliant minds together in the world of AI with the latest AI trends, technologies, and best practices to help you, our audience, in the world of AI. Today, I'm absolutely thrilled to be joined by some incredible guests and incredible speakers. We've got Arcturus Networks and NXP talking about how you can bring edge AI to life. And before I introduce our speakers, just a quick bit of housekeeping for those of you who are new to our Tech Talk series. Welcome, first and foremost, especially to you guys. The way this works, we're going to have a quick presentation from NXP and Arcturus. There's going to be an opportunity at the end to ask your questions, so please feel free to pop them in the Q&A box in Zoom, and I'll get to those at the end. As we do these Tech Talk series, we've also got one coming up in just a week's time. It's a bit of a jam-packed July. So we've got one coming up on July the 20th with Arduino, which is really, really exciting. And I'm also really thrilled to say that we'll be launching, we'll be taking August off, which is also great, but we'll also be launching some more Tech Talks from September to December very soon. And that includes a specific series for the Asia Pacific region. That's really, really exciting. You guys are the first to hear about it publicly. We'll be launching that in the next couple of weeks, bringing some of our partners and ARM presenters for that region as well. So do keep an eye out for that. Promises to be really exciting. So without further ado, I'm going to introduce our two speakers today, David Steele from Arcturus Networks and Ali from NXP. I'm really thrilled you guys could join us today. So David, Ali, over to you guys. Tell us how we can bring edge AI to life.
Thanks, Tobias. That was a great introduction. Hello, folks. Welcome. My name is David Steele. I'm the Director of Innovation at Arcturus, where I'm responsible for Edge AI and Vision programs.
And hi, everyone. I'm Ali Ors. I'm Director of AI ML Strategy and Technologies over at NXP Semiconductor for all our edge processing portfolio.
So thanks for joining us today. Why don't we take a quick look at the agenda for today. We're going to start with a quick introduction into edge AI applications. We'll look at a couple of samples and we'll talk about some of the challenges faced by developers. Ali is going to cover off edge tools and enablement. I'll introduce a couple of my team who are here as well. And they'll talk about building and scaling edge AI applications and applying ML optimization techniques. And then we'll give you a quick demo of a system-level solution that applies some of the concepts that we discussed. And we'll end off with how to enter the prize giveaway. For some of you, I'm sure that's going to be important too. So we have a lot of stuff to cover. So why don't we jump right in? So as Tobias said, the big question for today is what does it take to bring an edge AI application into the real world? And to help answer that, probably a good place to start is to frame a few edge AI applications. So these are a few projects we've worked on at Arcturus. These applications are part of a hardware software product line we call Brink Edge AI and Vision Analytics. These applications primarily focus on smart city public safety, but the underpinning architecture and primitives are really cross-domain. They cross from manufacturing to retail, really wherever a mix of real-time detection and local actions is needed. So on the top left, we have a straightforward zone incursion and boundary crossing application. It can do things like monitor people on a subway platform to detect crowding and make sure no one is at track level. On the right is our package analytics application. It's intended for smart cities. It can do things like detect abandoned packages in public spaces or transportation hubs. It can also do slightly less altruistic work, like monitor that Amazon package that just got dropped off on your front porch. This top row of applications are lightweight. They can run on a raw CPU with no specific AI acceleration. But on the bottom row, we have more complex applications. We have on the left characterization, which is a method to describe appearance attributes, such as what a person is wearing. And on the right, we have behavior analysis, which can range from simple loitering detection to much more sophisticated action recognition, such as detecting aggression or violence. Now, each of these four applications is very different. They all use different models, workflows, and pipelines to solve different problems, but they all share a common set of challenges from the standpoint of a developer. Now, the first challenge is really to understand that developing an ML application is very different than traditional embedded development. To solve a problem using ML requires considerable experimentation, adaptation, and iteration. Now, this is a time-consuming process, and this nuance, above all, can be very difficult to communicate to a management team. It's also heavily dependent on optimizations, including achieving the right performance accuracy balance for your application. And there are complex interdependencies across models, model training, edge runtimes, and even edge accelerator hardwares. So to solve these challenges requires a broad set of skills. Skills that are not only capable of applying ML to solve a problem, but also skills that can envision an architecture that can adapt and scale as experimentation leads down different paths. The second challenge is that existing starting points don't move seamlessly into production. And we sort of said this in the promo of this session. It's fairly easy to get a demo up and running on your PC, but what you might discover is that as you try to move it to production, the model you may want to use might not be supported by the edge runtime you want to use. It may not have all the model layers well optimized for the hardware, and this could cause bottlenecks. Perhaps the training and evaluation data that gave you early confidence may not be actually representational of the data that you're going to get in your application. And this could result in very good performance in the lab and very poor performance in the field. And you may also find that you have specialized requirements. You may need to add a class, and you will likely find it necessary to add additional algorithms, models, or heuristics to achieve a production grade determinism. So to be successful as a developer, it's good to go in with the expectation that solving your problem is going to lead you fairly far away from where you started. And there are kind of three considerations to think about. Number one, how do I take an application and move it to the edge? Number two, how do I improve accuracy and performance to achieve that production grade determinism? And number three, how do I develop an architecture that will adapt and scale to shifting needs? And that's really what Ali and I are going to try to address today. So I think with that introduction rife with expectation, let me introduce you to Ali Ors from NXP to kick things off here.
Great, thanks a lot, David. So we do have quite a bit of content to cover today, so I'm going to be going a bit fast, but all of this content is, of course, available to review. Just a quick summary of at NXP, what we offer. We are fundamentally a processor semiconductor company. In our overall portfolio, we have what we call the EIQ, Edge Intelligence Machine Learning Software Development Environment, which I'll be going into a lot more detail today. We do build third-party software and hardware. We have development boards, both internal and with partners that we host. We have turnkey solutions in our portfolio for voice and face recognition for advanced solutions like security, door features, access features. And we're also a very large supplier of the automotive space with automotive semiconductors. So we also have our EIQ Auto enablement toolkit, which brings in additional automotive SPICE compliance and some safety features in the inferencing and building units. But today's focus is going to be on the EIQ software that we have. On the overall product portfolio, as I mentioned, as a processor vendor, we have a very large, what we call the edge processing continuum, from microcontrollers, low-end, very resource efficient microcontrollers, all the way up to application processors with multiple Cortex-A cores, GPUs, DSPs, as well as now NPUs dedicated for machine learning activity and workloads. One of the first products in that portfolio with a dedicated NPU for machine learning is our i.MX 8M Plus, and that brings in a 2.3 TOPS NPU, which is all enabled with the EIQ software. And in the future, we have devices in our portfolio with the i.MX 9 family, which has been announced earlier this year. That brings in an ARM Ethos U65 in some of its variants in that family. We also have what we call a crossover. Is my audio coming through? It seems like some panelists are having difficulty.
I can hear you okay, Ali.
Okay. Yeah, I just saw. Okay, so, all right, thank you. And we also have crossover devices which have microcontroller Cortex-M class processors, but also bring in additional SRAM memory and GPUs into that space, and very power efficient and compute efficient devices in that portfolio. When we talk about machine learning and use cases, control's a bit lagging. Use cases and accelerators, we've mapped the applications to the type of processing needed, as well for different classes. A lot of today's machine learning workloads are vision-based, so camera input-based, and we see that depending on the complexity of your application, the type of processing you need, if we were to map it to a teraops per second type of workload, you can do quite a bit with a Cortex-M class device or even multiple Cortex-A based CPUs. And then as you start getting into a lot more real-time processing, a lot more objects and surveillance, which David and the Arcturus team will touch on, you end up needing a bit more performance. So you start scaling in both your compute engine needs as well as the performance in those engines and the memory bandwidth to it. Similarly with audio and time series data, the more complex the problem and the application you're trying to solve, the more performance you need. So there's always a sweet spot. And with the previous edge processing continuum that we presented, NXP has actually quite a good coverage across the board for these applications. The main talk today from my side is on the enablement aspect. So you need good enablement to be able to bring your applications to life, to bring it to the edge and into reality. The typical flow, if we left to right here, that we see is a supervised machine learning development flow, where you start with data. Data is extremely crucial and essential. You prepare and train with this data. Then you move into the validation stage, where you try to create a trained model. You pick a model and use your training data to create a trained model. And you go through an iterative process of optimizing and converting this model until you get a model that meets your key criteria of accuracy or performance as you need. And it is a recursive process. As you're fine-tuning, you might have quantization steps, other optimization steps that you go through and revalidate with. At times, it might not be sufficient, so you might have to go back to the training step to add more training data or to augment your training data. And once you have a converted model that meets your needs, your performance needs, you can deploy this onto a device, an NXP device, for your inference real-time perspective. The EIQ machine learning software covers pretty much all of this flow from the data preparation and training aspect all the way down to deployment onto the device and the validation of it. And once you're deployed on the device, you can still collect more data and improve your model performance by feeding it back and taking it all the way back to the training step as needed. The machine learning software that we offer under EIQ from NXP, you can pick and choose components out of this flow, or you can use the full flow for your needs. And that's where it comes into the machine learning software development environment, the EIQ toolkit, the EIQ software that we talk about. So this is the full view, where our goal is to enable machine learning experts, data scientists that are very familiar, but as well embedded developers that are just coming on to porting their applications over to an ML-based model potentially, or building their first machine learning-based solution. We try to cover the enablement for the variety of user expertise as it comes in. We have, with the EIQ toolkit, a workflow tools that allow you to bring your own data and work within the tool itself, what we call the BYOD, bring your own data workflow. Or you can bring a model. If you already have an existing model, you can actually port the model in and still leverage the tools in terms of validation and profiling. And at the bottom, we have various inference engines that are supported for the applications themselves. So you could actually choose to just leverage the inference perspective of the tools and pick your inference engine depending on the performances that you need or the specific use cases that you have. And for the MCU class or MPU class, so both for Cortex-M based solutions as well as Cortex-A based solutions, we have offerings. On the EIQ toolkit, which was the top of the previous image, this really is about easing the machine learning development environment. We have a GUI aspect called EIQ Portal, which carries out, especially for vision applications, the full bring your own data or bring your own model view. It creates, allows you to create, optimize, debug, and convert machine learning models. And on top of this, we also have what we call the EIQ marketplace. So all of the aspects of EIQ toolkit, EIQ portal, and the inference engines are part of our baseline enablement and come at no additional licensing fees. With EIQ marketplace, we're offering an option to our ecosystem partners and also really professional support and faster time to market for our customers to leverage some integrated solutions or to try out some of our partner solutions and offerings that are integrated with the EIQ software. On the inference side, we have a collection of open source community-based engines like TensorFlow Lite for microcontrollers, Glow compiler, or ONNX runtime. And each of them have certain benefits depending on how the base tool is implemented. And to this mix, we've added now, as of last week, we've announced the addition of the EIQ inference with DeepView RT runtime, which is an inference engine from our partner Ozone Technologies. And it offers a proprietary inference engine, which scales for a wide range of NXP devices. And the thinking behind offering a proprietary engine to complement the open source engines that we have is to have a stable and long-term maintained solution as well for customers that are in market spaces like industrial applications, etc., where they need a longevity of maintenance and an availability of product and enablement aspects. The inference engines are available as part of our Yocto BSP release for the application processors and the MCU Expresso SDK for the microcontrollers that we have. This is the overall view of how our inference engine enablement maps onto the different compute engines that we have in the devices in our family. There's a few more devices here that are not shown that we're always open to talk about additional support. But the key piece is that for a device like the i.MX 8M Plus that has a Cortex-A cluster, that has Cortex-M cores in it, has an NPU machine learning accelerator, has GPUs, has DSPs, we have all the inference engine enablement needed. Similarly, on the microcontroller side, with our i.MX RT family, a lot of that family is enabled through multiple inference engines so that the customer has a choice on their preferred method or whichever inference engine gives them the best performance or accuracy for their end use. The toolkit is now available. This updated EIQ toolkit is now available straight from nxp.com/EIQ, and we will be sharing these links at the end of the talk as well. Now, quickly to go into how the flow looks like, especially when you're using the EIQ portal and the GUI aspect. So this is your landing page. You have a full project creation, opening an existing project, working with the model tool. And you also still have the option to work with the command line. So if you prefer the command line and not the GUI, or you only want to leverage certain aspects of the GUI, that is an option that we've maintained. As I mentioned, we're trying to host and enable a wide variety of expertise levels from our users. And we do realize that a lot of users might prefer command line options versus a GUI, or might find it faster or more intuitive for themselves. So we host both, and they're interchangeable and are integrated. One of the key solutions that we provide as part of the GUI is what we call the data curation tool set. So you're able to import your data. So this is for the BYOD flow, bring your own data flow. You're able to capture, bring in data sets, annotate images within the tool, import and export, and also do modifications, and also select how to distribute your test data for how much of it you want to use for training and how much you want to use for validation and test perspectives. So this is a flower data set with different classes of flowers that is being used for an example. And on top of the curation aspect, you can also augment. So this allows you to apply certain filters to the data set and adjust image parameters so that you have more variety in the training set, in also the validation set, but also you're able to reduce overfitting and you increase the robustness of your resulting model with it. And all of these are available with to the user to control how much to augment and add variety to the data sets that you have. Currently in the EIQ portal, we have with the model tools a support for classification and detection models. We'll be expanding this. This is the first step in what we've released with in Vision solutions specifically. So classification is where you identify what is the most likely item, class of an item that's in the image. Detection, it's a bit more complex. It builds on top of the classification aspect, and Arcturus has very good examples of this in the follow-on section of this webinar. You can select one of these model selections. So this is part of the GUI. You can leverage an existing base model or import a model. This is an ever-expanding set of models that we have. And then you can optimize for certain corners. So you can choose to optimize for performance. So your runtime is faster, but it might be at a cost of lower accuracy potentially. Or you might opt for accuracy, and then your runtime latency might be slightly more increased, but you'll have higher accuracy. And these parameters are fed into the model training aspect, or you can choose a balanced option. So these are all click-through buttons. Beyond that, from your accuracy performance selection, you can also select which compute engine in a device to target. So between the Cortex-M MCU or the Cortex-A CPUs, GPU options depending on the device that you want to use, or an NPU if it's an i.MX 8M Plus or an i.MX 9 future product that comes in. Planned future functionality has further optimizations based on the actual compute engine specifics that will be available to that. And then once you have all of that selected, you start training. The GUI allows you to train for a specific accuracy mark or a given set of epochs and batch sizes. So you have all those selections to work through. And at the end, you get, you can actually analyze once you've hit your performance mark or your accuracy mark, you can analyze the model itself and see where you have room for optimization potentially, or what each step or each layer of a model is taking in terms of compute time, or is taking in terms of memory bandwidth. You can see where the best return on your debug time or return on your improvement time would give results, the best results. This is a quick video of some of the steps that I've been talking about. So as you can see through the GUI, you can select for classification, pick a balanced approach, then select which core, the microcontroller in this case, pick the image input size depending on the data set that you have, how long you want to train, what your batch size is, how many epochs to train for, and it's cumulative. So as you're training, if it's not meeting the accuracy, you can continue your training and then analyze. And as you start to training, you'll see the window update, and over the epochs of training, your accuracy should tend to go up as it moves through. And once you've trained, you have a validation option. So we get into validation options such as using a confusion matrix or class accuracy for what you've trained. With the confusion matrix, the goal is to get as much on the diagonal between the actual label of the image and the predicted label that your model provided. You want everything to be on the diagonal green boxes and be very dark green, meaning that you don't have mispredictions on the model. And if you do have mispredictions, you'll see that you have pink or reddish blocks depending on how many images were mispredicted here. The user has clicked to see why items that are labeled as daisies have been predicted as dandelions. And you can look at your training set. You can look at if there is something in the label to make it more clear, or to add to your training so that the prediction is more accurate, and you can analyze your results this way, all within a GUI. And then you can also profile and validate on different options. By default, you're validating on the model on your local PC. So it's really all just on an x86 platform with your PC. But if you have a remote device, if you have a board like an eval board or an actual board connected, you can also validate directly on target via the tool. So you can select a remote device to validate on and get your actual profiling done. All of that was covering the BYOD, bring your own data workflow from data in all the way out to profiled, deployed solution. We also have a bring your own model tool. As I mentioned, you might have your own models that you've already worked on with other off-the-shelf community tools, and you want to import it, or you're leveraging a research model and you want to leverage it and put it through its paces through the tool and then deploy it on an NXP device. We offer the BYOM model to bring your own model in. You can even convert that model if you want to see how a given model works with different inference engines. So here with the model tool, you can bring in TF Lite model in and convert. And we have a different model converter support within the toolkit, going from TensorFlow to DeepView-RT, for example, or to ONNX. And the tool gives you a lot of options on how you want to handle the conversion, taking a TF Lite to an RTM model, for example, and then deploying that and seeing different ways of quantization, different inference engine solutions, and how they impact your results, both accuracy and performance aspect on a deployed solution. So I'll hand it back to David. This is really a quick flow through, and all of this is now available on nxp.com/EIQ, and we'll have all those links available to you at the end.
Thanks, Ali. I remember Arcturus was a beta evaluator of the original EIQ, and it was a great tool to kickstart edge AI development back then. So it's amazing to see how it's evolved, and these features and capabilities look absolutely awesome. So now I guess now you understand how to apply custom models and domain-specific data to get solutions running well at the edge. What I'm going to cover off now is I'm going to move up the stack a little bit more and cover off what it takes to develop an application. If we go back and reference the application examples from earlier, a common foundation to them all is that they're running a combination of networks, models, algorithms, and heuristics. In fact, all four of these applications benefit from using object tracking. And tracking is a pretty common foundation for a lot of applications. So why don't we just take a quick look at what it takes to implement tracking in a real-world application. Now, the simplest approach is motion tracking, which predicts where an object will be in the future based on its vector. If an object appears within a prediction envelope, then it gets assigned to the same identity. If it does not, it gets assigned to a new identity. This method is quite fast, but it has a couple of limitations, not the least of which is it can only track objects that remain in the field of view. So if an object leaves and comes back, or if a track is lost, the object will get identified as a new object when it reappears. This also means that motion tracking is very dependent on constant and accurate detections, and that makes some models better suited than others, especially when it comes to small objects, crowded scenes, or partial occlusions. So to address the limitations of motion tracking, what we can do is we can add a visual appearance embedding. This provides a feature vector of the object's appearance. The feature vector can then be used to re-identify the object, basically irrespective of time or space. But to do this, each object needs to be detected, and then each detection needs to be processed by a separate embeddings network. So this means that we're now running two networks. It also means that the more objects in the scene, the more processing is required, which can become a bottleneck as the scene becomes busier. So at this point, tracking has now become a good example of a simple task that's grown in complexity as our experimentation advances. And the result is that we've introduced two networks, and we've also created a scalability limitation by developing a non-constant time system. And frankly, we haven't really got that far along developing our application yet. With that problem hanging over our head, what I would like to do is introduce two of our Edge AI experts, Harshad Mohadik and Jonathan Rin, who are going to talk about building and scaling pipelines and optimization techniques. Harshad, I think you're going to kick things off.
Yes. Hope you guys can hear me and see me well.
Loud and clear.
All right. So now that we know most real use cases will likely require us to run two or more models concurrently, how exactly would a developer build, configure, and run such a pipeline? So at Arcturus, we've been working on an SDK. We call it the Brink Edge Creator SDK for developers to be able to do just that. Basically, we split all of the processing into logical nodes, where each node will perform a specific type of work. So constructing pipelines with this SDK is very similar to, if you ever use GStreamer and you're familiar with the notion of different GStreamer elements forming a video processing pipeline, it's very similar to that. So in our SDK, there are 3 types of nodes: source, filter, and sync. And the pipeline can have 1 or more of these. Each node will have a corresponding configuration file. It's a JSON file which will configure all the settings with the input and output streams, IP addresses of them, etc. So let's take a look at the tracking pipeline. There are 2 models that you need to run: object detection and embeddings generation. So first, we'll run both of those on the CPU as a baseline, and then we'll offload the object detection to the NPU, and then let's see the performance. So here I'm configuring the accelerator to be CPU, and we should be able to run the model, the full pipeline, including the object detection and the tracking. I'll redirect the output to output.log, and I'll just grep for the right keywords so you can see the performance. So you can see all 4 cores are going strong. If you look at the source FPS, it's 60. If you look at the object detection time, 131, which is around 7 to 8 FPS. And that's the performance on the CPU, right? So let's kill our pipeline, change the accelerator to NPU, and let's see how this changes things. So this time we'll have to wait slightly longer because there's an initial warm-up time for the model to get going and the inference to actually run on the NPU. But once it's warmed up, you'll see that the cores aren't as utilized as they were before. And we'll stop so you can see what the actual inference FPS is. You'll see that it takes 30 milliseconds, which is around 28 to 29 FPS. So this is a night and day difference in performance. So you can go from, and yeah, I call it great success. And so that gives you an idea of how easy it is to, at runtime, do things like change the accelerator backend, experiment with various types of settings. And that's a brief look at our Edge Creator SDK as well. So what I'll do is I'll throw it to Jonathan. He's going to go into more of the ML techniques that can be applied. Jonathan Wren is one of our data scientists at Arcturus, and he's going to cover some more additional optimization techniques.
Thanks, Arshad. Thanks for the intro. So as you guys probably have gathered from some of the previous workflows and pipeline diagrams, these systems are slowly starting to get a lot more complex. And you're definitely going to start to run into certain issues, especially when trying to, maintain that real-time system. So more specifically, you're going to start to run into latency issues, especially when you need to run more than one model. So the question kind of arises, how do we keep a system real-time and reduce these latency issues? And how do we solve, the bottleneck issues that we're seeing in a pipeline where a model needs to be run more than once for a certain frame? So a common solution that a lot of people turn to is to just use a more lightweight model, which isn't a bad solution. But what if using a different model isn't feasible, or the MAP of the new model that you've chosen is lower than the one that you were using before? So we start to see how this performance versus accuracy issue arises. And it just begs the question, how do we optimize these workflows to squeeze the best out of accuracy and or performance based off of the user's needs and the system at hand? So depending on what you're trying to achieve, you could use some or all of the techniques that are listed on this slide. We have concurrent processing, batch processing, model depth reduction, which are usually used to target the performance, increase the performance of your system, whereas a method like tiling is going to be used to increase the accuracy of your system. As always, there's network quantization, which is probably a full tech talk in itself. So we're not going to touch upon that today, but it is a common technique that is used to increase the performance, but it does come at the cost of decreasing the accuracy. So I'm going to start today by just taking you through the first two techniques. So starting with concurrent model processing, this is, like I said, used to increase the performance of the pipeline. Simply put, it's just executing two or more actions at the same time. Now, for the purpose of relating this to what we're talking about today, we're going to say it's the process of executing two or more models at the same time. So these can be two different models, like an object detection model and a segmentation model, or it can be the exact same model that's run multiple times. So if we look at the latter, just to see how concurrent processing might be beneficial when needing to run the same model more than once, let's take the embeddings model that Harshad and David were talking about, which is used to generate an appearance vector for each person in the frame. This model needs to be run once for each person. So if we have 100 people in the frame, you're going to need to run this model 100 times. So we can slowly start to see how this begins to create a bottleneck in the overall system. Now, to reduce this bottleneck, we're able to create multiple processes to run these networks concurrently while worrying about syncing the data afterwards. So if we're given, an image with 4 people in the frame, and we're using MobileNet v1 as the embeddings network, the original method will take around 120 milliseconds. So that's your 30 milliseconds inference time multiplied by the 4 people in the frame. Now, if we were to go and implement concurrent processing, we can actually reduce this time in half to around 60 milliseconds, where you get, of that 60 milliseconds, you're going to have the 30 milliseconds for your original inference time, and then an extra 30 milliseconds, which is like the resulting overhead from running these models concurrently. So not only does this help us achieve the original goal of reducing the latency, but it also actually increases the throughput of the node. So when you have an increased throughput, you're naturally going to have a higher FPS for that specific node. And if that node is running at a higher FPS, you can usually see an improvement in your overall system performance. Also, when you have a higher FPS, naturally any following analytics that you do decide to run, such as tracking, you'll usually see an improvement in that just because you've increased the number of frames that you're actually processing. So this all sounds great, you've reduced the latency and whatnot, but this still might not be the best solution for every situation. With concurrency comes increased complexity. You're going to need additional memory management and IPC techniques to be able to sync this data and bring the system back up to a working state. There's going to be increased memory consumption to run a direct copy of this process. And finally, this method can be very resource intensive, depending on whether you're running it on the CPU, the NPU, or the GPU, or a combination of any of those. So depending on the resources of your system and how limited they might be, you can definitely experience varying inference and pre-processing times. So why don't we have a look at a different method, that's a little less resource intensive, but can still be used to increase the performance and reduce the previously explained bottleneck. Yeah, so this method is called batch processing, which simply put is just, when items are grouped together and are going to be processed at a later time. And this typically results in little to no user interaction. So if we want to relate this to what we're talking about today, again, this is the process of grouping images together and running inference on them with a single execution command. And this can often be referred to as runtime batch inference. So if you have a model, with a batch size of n, and you're actually able to collect and store n images, load them into a single input tensor, feed them into the network with a single command, and receive a single output tensor. So it really does, start to simplify things from the user's point of view. Now, if we have a look at this graph, though, you can see that there's an increased throughput, but there's also an increased latency. So even though the model is still executing each frame sequentially when batching, and typically we don't see any performance increase with the inference time itself, we do see an performance increase with the pre-processing time. So since we're only loading one input tensor, regardless of the batch size or number of frames being processed, that's where we see this decrease in the pre-processing time. as mentioned, you do see the increase in latency with the orange line, which actually starts to go up pretty fast as the batch size increases. But this is usually expected with most methods of batching, just because you're processing more data at a single point in time. So it's not a huge concern, but it does kind of raise the question, why would you ever want to use batching in a real-time system if all it does is increase the latency? Or, when would bunching a bunch of images together ever be faster than just running inference frame by frame and dropping the frames in between? So if we think back to the previous example I gave with the embeddings model, and we have a number of cropped images of people as the inputs, we actually have this data readily available at the beginning of each process. So if you take a step back, look at the bigger picture, the latency of that embeddings node itself has actually been reduced. So batching is definitely a lot less complex than the concurrent processing that you guys saw, and it simplifies your system with the single input and output tensors. But like every other technique, it will have its drawbacks. So depending on the size of your batch or where and how you load it into memory, you're going to see an increase in the RAM consumption. That's just inevitable. Another drawback is the model and the backend compatibility. Does the model you're using even support a batch size greater than 1? Does the backend, such as ARM&N, TF-Lite, or TensorRT, does it support dynamic batch sizes, or does it support fixed batch sizes? These are all questions that definitely need to be considered when you're trying to implement this batch inference. And of course, you do have the increased latency, which can definitely hinder your system, depending on what you're trying to use the batch processing for. So when would you, want to use batch versus concurrent processing? I typically like to think of batching as an ideal technique when you have limited resources, or if you have a large number of inputs, whereas concurrent processing is going to be probably the better route to go if your inputs are reduced and you're not as tied down by your resource availability. So if you have 10 inputs, 10 cropped images of people, you don't want to go and spawn 10 new processes concurrently. But if you only have 10 inputs, simply creating a new process might be the most efficient method for you. On top of that, you can always just create a hybrid method of the two optimization techniques that might best suit your system. And finally, another great use for batching, which I actually find very interesting, is when it's used alongside another technique called tiling, which I'm actually going to pass over to Harshad now to dive a little bit deeper into.
Awesome. So what's tiling? If you think about tiles on your floor, I'm sure you at least have one floor with tiles. And let's just assume they're all the same size. It's basically that. So if your floor is divided up into tiles, it's you take an image, you divide that up into tiles, and you run inference on each of the tiles. And what that allows you is, you can see an example in the picture on the left is the whole image. If you run that through the inference engine, such as MobileNet SSD, the person and the suitcase are so small that it's not able to detect those two. But if you tile them, it's able to detect them, even though the confidence is slightly lower. So it definitely is a good approach for simple networks like SSDs to improve the small object detection. And with detection, as David Steele mentioned, as long as you have a good detection accuracy, you can have good tracking, because without detection, there is no tracking, right? But it's not all good. So if you look at where the shortcomings are, so you'll see that the image on the left, it's able to detect everything. You think it's able to detect everything, but the image on the right will show you that there's a minute detail there, that there's a tie as well. So that's cool. But what did it also detect on the very right? It's a false positive, right? And you can see that it's a lower confidence than the rest of the detections. So it does increase the number of false positives. And one way around that is to have a confidence threshold per class. So if tiling increases the person confidences, and most of the actual positives are true positives are higher than 80, you can probably set the confidence threshold to 80 and get rid of the false ones. And it also obviously adds the pre and post overhead to split the image and then recombine the detections. So tiling is definitely one avenue to explore if you're stuck with a simpler network where you like the the performance that you're getting, but it's not as accurate on smaller things. But you need to be aware of the side effects as well. So another technique, which is kind of a sure shot way of improving performance, is the model size depth reduction. And this definition, the best place to get the definition is obviously a comment in the source code. So this is what I found. Depth multiplier, essentially a multiplier for the depth for all of the conv ops. And naturally, what that does is, if you look at the first row in the table there, if MobileNet V1 at its 100% gives you 51 milliseconds of time per embedding with an accuracy of 63. If you slim it down to 75%, you can go from 51 to 33 milliseconds per embedding. And if you slim it down even more to 25% or to 50%, sorry, that should be 0.5, which is 50. You go down to around 19 milliseconds. And if you look at the accuracy, it's not that much of a hit. It goes from 63.5 to around 60. So as long as you're okay with that accuracy drop, me personally, I would absolutely go for a slimmer network if the accuracy drop is within a few percentages, right? So that's one sure shot method of looking at improving the model performance. And just to be clear, the calculations were done on a 4-core, quad-core ARM Cortex A53. And with that, I'll pass it on to David Steele to do some more good stuff.
Thanks, Harshad. So I know we're getting pressed for time here. I'll try to move through this quickly. So far, we've illustrated why your needs might change during development. We've illustrated how to build and modify a pipeline to offload processing from a CPU to an NPU just by changing one letter in a JSON file. And we've provided some insights into optimization techniques to improve performance and accuracy. But what if our needs were even more complex than this? What if we needed to run more than 2 models or process multiple video streams? Or what if our workflow was more sophisticated than just object detection, perhaps beyond the capability of just one SoC or NPU? And characterization is a good example of this. Here we have 2 models, an object detection model and a more complex segmentation model. And together, their role is to characterize what a person is wearing in real time. Looking at the workflow, we can see how the 2 networks work together. The object detection model outputs class and localization, in this case, a person with a bounding box. And the segmentation network outputs the probability that each pixel in the image belongs to a given class, in this case, clothing. When combined, the object detection acts as a way to hone into the pixel-wise classification, making it possible to determine what the person in the bounding box is actually wearing. Once a person is detected, the pixels from segmentation output get sampled and fed into a color model, and this provides the final output, which is object detection, clothing class, and clothing color. And this is pretty neat stuff, but to get performance and accuracy plus real-time processing, we'll likely need the resources of more than one SoC. So how do we accommodate that? Well, if we look at hardware first, we can look at a platform like this. This is Atlas. It's one of our Brink Edge AI hardware platforms. It's a modular Edge AI system that can scale from 4 ARMv8 cores to 10 ARMv8 cores with additional ML acceleration using NPUs and GPUs. Uses 2 SoCs from our partners at NXP and NVIDIA. And the 2 SoCs are connected via a dedicated network fabric. Now, this is a pretty big workhorse of a platform. It can provide up to 23.3 TOPS. And for those of you who don't like TOPS as a metric, to put that in real world context, that's about 187 frames per second using MobileNet V2. And because it's modular, we can scale it to meet our price performance needs. We're not overbuilding edge hardware. We're not locking ourselves into a rigid design. And this is a good approach because it can adapt as our needs change. And we don't need to wait for a full design, production, and qualification cycle to get software up and running in it. All we have to do is build software that can span across CPUs. And this diagram is the characterization workflow, but this is now broken down by resource using Atlas. On the top is the 8M Plus, and below is NVIDIA. Connecting the 2 is the network fabric. As Harshad illustrated early on, the pipeline architecture we use consists of discrete nodes, and these are interconnected using sockets. This approach has a key advantage because it's able to span pipelines across SoCs simply by moving from local host sockets to external network sockets. And that way we can actually take advantage of the 8M+ high-speed object detection using the NPU, and we can rely on the 21 TOPS of GPU performance NVIDIA gives us by running the complex segmentation network on that. Then we can combine these together, we can create the output, add our tracking, UI, UX, and services. Now, the other key benefit of having a pipeline built this way is that it's effectively a microservices architecture. And with microservices architecture, we can leverage pre-existing tooling to manage it. And that's where Docker comes in and all the Docker icons you see in this slide. Docker makes it possible to change nodes easily without destabilizing the system, whether you're doing that for experimentation or in the field. And so in summary, a pipeline architecture like this helps accelerate development by providing flexibility. It provides scalability to move nodes around and mitigate bottlenecks. And it improves serviceability by making it possible to upgrade software at a really granular component level. So we've told you how you can do it. I guess we better show you a demo of it working. That's the logical next step. For this demo, we did what every good AI company does, and that is get some young and eager interns to shoot some sample video for us. We were interns once too. We understand how that is. So here is our UI UX, which is running on our Atlas platform. The live video for this demo is in a loop, and it's being streamed from another machine just as if it were an IP camera. There are two main panels here, a live view and a playback mode. On the left, there are incident notifications of the analytics applications that are running. In this case, we have abandoned package, boundary crossing, loitering, motionless behavior, and intrusion analytics. You can see them, if you click on them, you can see the most recent incidents. Then on the right, there is a settings menu. And using that settings menu, we can change the video source. We can tweak detection parameters. We can even change backend networks or create an activity schedule. And there's also an option to build a region of interest zone. And you can do this fairly easily just by drawing it directly onto the frame. And you can mark this as a privacy mask or an area that you want to look at doing specific detection. And then you can just save that. We can also turn on bounding box overlays, and this will present the detection metadata. This will display both the track ID and the characterization information in the live real-time view. So you can see the metadata appear there. We can jump to the playback mode. On this view, there's a timeline of incidents, and below a list of incidents that corresponds to the range that's currently selected from within that timeline. There is also a search function that allows us to filter by analytics type, date, time, region, and characterization criteria. For example, we know that there's a guy wearing a green shirt, and for sure he's been up to no good. We can just run a quick search for a green shirt, and this should return us some search results. And we can click on the one of the search results, and that will return us the video clip of where that person appears. And we can play that video clip, and you can see the guy in the green shirt, and we've got his metadata as well, including his tracking ID and also what zone he's currently standing in as well. Okay, so that illustrates just a very simple use case for characterization and why you might want to run multiple networks across more than one SoC. Why don't I turn things back over to Ali to start to wrap things up?
Thanks, David. In the last few minutes, I just want to plug in, we do have an extensive series of training, self-paced training and walkthroughs around both EIQ software, as well as using NXP devices, the i.MX RT devices, or the i.MX 8M application processors on nxp.com/ml training. So please do check it out if you have further questions or want to learn more of how to use those. Yeah, we can go on to the links, David. And these are the helpful links, both from us and Arcturus, on pretty much everything that we've talked about today in the EIQ toolkit, the training, the community for support, as well as if you only want to leverage, there was a question around if I don't want to use the toolkit, can I just deploy a machine learning model onto an NXP device? That's through the BSP for the application processors or the MCU Expresso SDK. And you can build the SDK with only the pieces that you need for your MCU device. There was also a question on TinyML. So TinyML on a Cortex M class microcontroller, definitely possible. We have, within the processing edge continuum on our side at NXP, you have multiple devices in the iDataMX RT family that are enabled for machine learning, and you can deploy TinyML models onto those as needed.
I just wanted to jump in quickly, finally, for those interested in the contest giveaway. We're giving away two $250 Amazon gift cards, courtesy of Arcturus and NXP, for registering and attending this live session. Now, because of privacy reasons, we can't just draw two random names from the attendee list. So we need you to jump through one more hoop, and we do apologize about this, but we do respect your privacy. So get your phones out and take a picture of this Google link form. I think Tobias is also going to send out the link in chat. You have a couple hours to sign up for this before we close the registration, and then we'll do the prize draw, and we'll contact the winners directly and via email. So I think that is basically what we wanted to cover off. I'm going to hand things over to Tobias. Maybe I should leave this slide up just for a couple more seconds.
Absolutely, leave it up. Absolutely. There's a giveaway, guys. Let's go for it. Wasn't that awesome? Wasn't that an awesome presentation? Absolutely fantastic. Fantastic, guys, from all of you at Arcturus and NXP. A great presentation, and one that absolutely love following along with. We are coming up to the top of the hour, and Ali, I know you touched on a couple of the questions already. I'm just trying to flick through and think if there's one question out of those you'd like me to take that we can ask live. Are there ways, I'll take the one that's literally just, just come in. See if we can get to actually. Ali, on your side, is there a way to deploy my MATLAB deep learning project into NXP controllers?
Definitely. I mean, from the MATLAB output, depending on the model you get, that can be brought in with the model tool, or can be plugged in. We do support TensorFlow framework inputs, as well as ONNX Exchange inputs. So depending on what you output from your MATLAB tools, those could be brought into the EIQ toolkit flow with your bring your own model, or you can still leverage the inference engines as needed as well.
Thank you. That's great. And then I believe, and apologies if I get this wrong, from Vignesh's question, apologies for mispronunciation if I have. Are there ways to track the deployed model performance over a period of time? So identify if there's drift in the model performance over a period of time requiring retraining. David, I think that one's for you, given it came in during your slot.
It may be more of an Ali question, actually. I don't know, Ali, do you have some thoughts of that off the top of your head?
So on a deployed system, I think there's ways that you could bring back, run analysis, and then look at bringing back maybe additional input to your training. But I think, David, as well, on your side, with the actual deployed applications, there are ways of tracking results and updating models too, I believe.
Yeah, I mean, Harshad, Jonathan, I mean, one of the techniques to do that is to just continuously update your field data and train your models in the background, and then use something like one of our pipelines to change your Docker container that has an updated model in it. Harshad, Jonathan?
Yeah, I can pop in. So we have a time series database that records all of the activity and all the statistics for the inference filters and for the embedding filters. So you can always know if at a certain frame or a certain period of time, your inference time or your embeddings time kind of shot up. And you can do analytics and see if the system load was higher, or were there more people in the frame, etc. Right? And then there's also cases where there might be false positives, false negatives. Now, right now, we don't have a framework to dynamically improve the model, but it's a matter of getting those back in, retraining the model, and as David Steele said, doing a live deployment so that you don't have any downtime. So we do have developing support for it. Yep.
Awesome. Thank you, guys. We are just running over, and I think we can have one more question answered, if that's okay with the presenters, or are we, I don't, going into extra time here, using analogy from Sunday. Apologies, that's bringing back bad memories. So, can you please, this is from Mahesh, please apologies for myself if I mispronounced the name. Can you please provide the input size of the images that these numbers are quoted for? So not just camera resolution, but the actual image size sent to NPU or CPU for inference. I think that's for David when you were doing the
demo, but we can feel that. So I think I'm going to defer that to Harshad. But I mean, generally speaking, the model sizes can change based on the model that you're using. But I think we can give an example for MobileNet SSD, which I think Harshad is at 240 by 240. Is that what's the?
So the classification or the embeddings model is 224 by 224. It's 224 by 128 for the embeddings, or for classification 224 by 224. I think the MobileNet SSD that we always refer to is 300 by 300. So these are all off-the-shelf standard sizes.
Awesome.
And Tobias, I think there's one more remaining, so I'll just answer
yes,
that
Ali, go
from
for it.
Abdel Karim as well. Just I know we're in extra time. For the EIQ inference solutions, will the multiplicity of supported inference engines, is that having performance variation for the same accelerator with the same / different problem domain? And the answer is yes. So depending on, even for the same given model, taking it into a different inference engine, we're seeing variations in the latency, and we're seeing variations in the frame rate, as well as variation in the accuracy. So with the EIQ toolkit, you're able to profile across these different inference engines for both the performance and to also validate the accuracy metrics that you're trying to hit, and pick the best inference engine for your model and your end solution and application as needed.
Brilliant. Thank you so much. We've got through extra time. There's no penalty shootout. Fantastic. I'm happy. So no, brilliant. Thank you guys really so much for an awesome presentation and for fantastic answers to those questions. Very quickly before we end, and again, do enter the giveaway. The link is in the chat as well. As usual, if you're familiar with these tech talks, we do run, ARM does our own little prize draw at the end. So there's a little survey we ask. Please do fill that out. We'd love to hear your feedback on how we can improve these tech talks. We want to make sure we deliver the best content and platform for you guys. And we'd absolutely love to hear your thoughts and feedback in that. So please do enter that, and we'll draw someone at random for an Arduino board there. Very quickly, also on Dev Summit, David, if you wouldn't mind flagging up the next. Oh, sorry. Yep. Don't forget as well, Arduino talk next week, and this list will become a lot longer as we'll be scheduling talks from ARM and our partners in September all through to December, including ones for Asia Pacific. So do check those out as well. You'll hear from us in the mailing lists if you're subscribed to those. And then I believe it's Dev Summit next. And I think so. There should be a Dev Summit slide just coming up. Brilliant. Yes, thank you so much. There's Dev Summit coming up October 19th to 21st. So there's a call for papers out at the moment. There's you can learn more at devsummit.arm.com, and there's actually you guys are presenting, I believe, at that.
Yeah, I was just going to throw in a shameless plug there. Sorry.
No, not shameless at all.
Yeah, we'll be presenting an extension to this session actually. So this is really a primer for that session. Yeah.
Absolutely. So if you like this, go, make sure you tune in. We're also going to be, there's also a competition, a Dev Summit competition. So we're really challenging developers and engineers to think about how your technology can drive sustainability in our lives. And this has got to use ARM technology and your skills to design and produce a prototype that tackles a real life sustainability issue. There's some great cash prizes involved as well. So do check that out. It'll be at the devsummit.arm.com link, and just look for the competition there as well. So that is everything. I think we are all done. So David, Ali, Jonathan, Harshad, thank you all so much for joining us today. Thank you guys who have stayed on into extra time as well. And we look forward to seeing you at our future AI Tech Talks for all the latest in trends, technologies, and best practices in this broad world of AI. David, Ali, Jonathan, Harshad, thank you all so much.
Thanks, Tobias. Thanks, everyone. Bye.